Okay, the first speaker this morning is Adela Vraciu, and she will speak on possible values of F-pure thresholds of homogeneous polynomials.
Thank you. I would like to thank the organizers. It's a great pleasure to be included in this celebration of Karen's work. This is joint work with Karen, and it is actually an offspring of the WICA project that we started in band that Janet mentioned yesterday. So let me just start with some definitions. This will be entirely in positive characteristics. So K will be an algebraically closed field of characteristic P. F will be a homogeneous polynomial. I mean, the definition does not require homogeneous, but all the results that I will talk about will be in the homogeneous case. So M just means the ideal, the irrelevant ideal. And I said that the characteristic is a positive number, P. This notation, the bracket power, means the ideal generated by the powers of the variables, and it raised to the power of P to the E, a power of the characteristic. That's homogeneous power. So the goal of the F-pure threshold is an invariant that can be used to classify varieties of hypersurfaces in my particular case according to how singular they are. And as Janet mentioned, the actual invariant that we will study measures the singularity of the affine cone over the hypersurface defined by F at the cone point. So anyway, we want to classify the polynomials of the varieties according to how singular they are. And just a basic observation, the most basic measure of singularity is just the degree. So the higher the degree, the more singular your hypersurface. Degree or multiplicity, whatever you want to call it. So higher degree means worse singularity. But of course, there are finer invariants that can distinguish between two different hypersurfaces that have the same degree. And so I will just say something about characteristic 0 right now, and then I'll forget about it for the rest of the talk. In characteristic 0, it's the log canonical threshold that can be used to distinguish between hypersurfaces of the same degree. In characteristic 0, the log canonical threshold is the final invariant, and in characteristic P, we have the F-pure threshold, which we can think of as just a characteristic P analog of the log canonical threshold. I'll say more about that in a minute. But I'm not going to give the definition of the log canonical threshold, but it can be defined in various ways over the complex numbers using integrability, or more generally in characteristic 0 using resolutions of singularities, while on the other hand, the F-pure threshold in positive characteristic is defined using the Frobenius homomorphism. And the one thing to keep in mind is that it's sort of the opposite of this behavior, meaning smaller values of that invariant correspond to worse singularities. smaller values correspond to the worst singularities. And there's a sort of inverse relationship between FP threshold and degree, which I will say a little bit more about in a minute. There is this method of reduction to characteristic P, which gives the more precise statement of the connection between these two versions, which is, I guess it's a theorem of Hara and Yoshida, 2003, and also Takagi and Watanabe. Which says that if you start with something in characteristic 0, so the F is over a field of characteristic 0, but then you reduce it mod P, then the non-canonical threshold is the supremum of the F threshold of the reductions of F mod P over the various prime numbers P. And it is conjectured, I'm not really going to say much about it, but it is conjectured that for a fixed F, there are infinitely many P's where the F threshold of the reduction mod P coincides with the log count threshold. So for fixed F, there are infinitely many. I don't know if there's anything really known about this. I don't know much. I'll say something a little bit related to it, but I don't know any results. Except we know examples. There are infinitely many prime numbers P such that it equals to holds. And so just to write an example of that. Which sort of illustrates the nature of the results that I will talk about. So in the example, F is x squared minus y cubed, and it's known the log canonical value is 5/6, which, by the way, this is not standard homogeneous under the standard bracket, but it is homogeneous if you make the degree of x be 3 and the degree of y be 2. And this 5/6 is just the degree of x plus degree of y, that's 5, and divided by the degree of y, which is 6. So that's kind of the general phenomenon that I will talk about. Except my polynomials will be standard graded for the rest of the talk. And then what's the F threshold? Well, that depends on the characteristic. So the same F, but now over a field of positive characteristic, is going to have F threshold equal to 5/6, same as the log canonical threshold if P is congruent to 1/6. And something else, slightly smaller, it is 5/6. But again, for infinitely many P's, it's the same. For other P's, it's slightly smaller. And in fact, what this is, it is a truncation of the base P extension of 5/6 in base P. Okay, so let me give the definition of the F threshold, and then we go from there. We see what we can prove about it. But anyway, the question that I was interested in was, well, so first of all, the week our shop studied what we call extremal singularities, which were the ones that had the smallest possible F threshold relative to a fixed degree. Those were the continuous forms that Jared mentioned. Yes.
Sorry. Is FPT in general the truncation of the log canonical threshold?
I'll say something about that. Yes, with some assumptions. I don't know if it's going to be a truncation of this number where it's the number of variables of the sum of the degrees of the variables divided by the degree of the polynomial. I don't know if that's always the log canonical threshold.
Can I say it's variables?
Sorry?
Can I say it's
Yeah,
variables?
for my so that's with some assumptions. Okay, so here's the definition. So the FTP of F is two equivalent ways to describe it. It's the supremum of n divided by p to the e, such that f to the n belongs to this continuous power n to the p to the e. No, such that it does not. But it's also the same as the infimum of n over p to the e, such that f to the n is in the continuous power. This is not the original definition. The original definition, which was introduced by Takagi and Watanabe, was a threshold beyond which the pair fails to be F pure, but I'm not going to define what any of that means. This definition is much simpler and easier to digest. And what I said earlier, there's some sort of inverse relationship between this and the degree. Just a comparison, I guess. We would think of the degree as the largest B, such that F belongs to the ordinary power of the relevant ideal. So I could rewrite that as, if I wanted to, as a supremum. I'll write Q, I guess, instead of P to the E. So it's a supremum of the Q over N, such that F to the N belongs in N over P. So if you look at 1 over the degree, it would correspond to the infimum of those fractions, if you like P to the E instead of Q. The only difference is that here I have ordinary power instead of continuous power. So we would expect that larger degrees would give rise to smaller values of the Q threshold, and indeed that is the case. So I will say a few basic facts. Now, so the basic facts. First one is that this is always less than or equal to 1, I mean, provided that F is in the ideal generated by the variables, which I know there's assuming that it is. And I mean, the proof of that is easy. You can take for a fixed p to the e, you can take n to be equal to p to the e, and because the convenience is a homomorphism, f to the n is going to be in this ideal. So the n over p to the e is equal to 1, and it gives and there are other natural bounds as well, lower bounds as well as upper bounds. So now, what about the relationship with the degree? And for this statement, I don't necessarily need F to be homogeneous. Just the degree means the smallest degree of a homogeneous component. So just what I said here, the largest power of the maximal ideal that contains it. So if the degree of F is D, then the FTP of F is greater than or equal to 1 over D. So in some sense, if you fix, and this is going to be the setup for the rest of my talk, I'm going to fix a degree D, and I'm going to look for what are the possible values of polynomials, of FPDs of polynomials that have degree D. So in some sense, this is the lowest bound, it's 1 over the degree. However, that is achieved precisely when expressing that's different only dimension. F is the power of a linear. Now, for my talk, we will be interested in reduced polynomials, so that's excluded for that reason. Or isolated singularities, which for most of the talk I will focus on the case of two variables where reduced is the same as isolated singularity. But in any case, this value will not be allowed because it's not reduced. So that's also very easy to prove. But maybe I'll skip that. The point is again, you fix a p to the e. So I'll just give a hint. Could be an exercise, but if you fix p to the e, I'll call it q. We can take n and e, I guess, to be the ceiling of q divided by d minus 1. And then when you take f to the power, it's not going to be in the Frobenius power, in the n to the bracket q, which gives a bound. And then you take the limit. When it goes to infinity, that's how you get 1 over d. The limit of this n e divided by p to the e is 1. And then in a similar thing, but an upper bound now, I don't know, I have always found it. I have a 5 in my notes, but I'm skip some of the other ones. So it's 3. Now f is homogeneous. Again, degree d, and n is the number of variables. Then the activity of f is now less than or equal to n. And again, the proof is along the same lines. You fix a p to the e, you pick n. So I'll just say the hint. You pick n to be again the roundup of n times q divided by d, something like that, yes. And then you see that when you raise f to the power, every term in the expansion contains at least one exponent that's greater than or equal to q, meaning dt is automatically in the bracket power. Yeah, I have a comment about the largest possible value. So I think I gave two upper bounds. On one hand, it's less than or equal to 1. On the other hand, it's less than or equal to n over p. So the largest possible value, I guess, is, again, for a fixed value of n and d, the largest possible value is the minimum between those two bounds. Well, I guess I wanted to refer to when is it equal to 1. And larger values correspond to milder singularities. In this case, value of 1 corresponds to f pure singularity. So just as an observation, the f is 1, if and only if the singularity is f pure. But again, I don't want to go into what that means. But we do have this criterion, Feder's criterion, which says that is if and only if f to the power p minus 1 does not belong to the bracket power p. So this might be a little surprising, because if you look at the exponents here, if you think of this as n and this as p to the e, it gives me p minus 1 over p. So well, I guess one implication is clear. If the FTP is equal to 1, then you cannot have that, because that would contradict the 1. But the inverse is a little bit surprising, I suppose, because this assumption would just mean that the FTP is greater than or equal to p minus 1 over p. So how do we get 1? Well, I have to prove in my notes, but I'll skip it. In any case, the proof shows that it's not possible to have anything between p minus 1 over p and 1. So that's what there's a theorem, I guess, which again I'm not going to write it, but there's a more general version of what I'm looking at, which says that there are certain forbidden intervals that cannot contain any values of the pure threshold, and that's a theorem of Brickell, Mustafa, and Steels, 2009. So anyway, this phenomenon here illustrates one of those forbidden intervals between p minus 1 over p and 1. So there are no possible values. Of the expression in the interval 1. Let's see, maybe. Anyway, so there's more such intervals of a similar nature, but let's not go into that necessarily. And so anyway, the question that I want to address is, if I fix n, d, n is the number of variables, d is the degree, and p is the characteristic, can we say what are all the possible values of f? And I guess I'm not ready to say all the details, but there is a theorem of Hernandez, Nunes, Betancourt, Witt, and Zhang that gives a lot of information in that direction, but in particular they give necessary conditions. So in particular they say, I guess I'll say it now, but I'll say it later in more detail as well. So Hernandez, Nunes, Betancourt, Witt, and Zhang. It says, so they do have the assumption that f is an isolated singularity, in the case of two variables reduced. So they say that the possible values of the FQT of f is either equal to n over b or a truncation of the base p expansion. So I will use this notation. And over the truncated at the L start, meaning to just keep the first L digits in the base P expansion of N over D. And they give a number of necessary conditions for that L. So not every spot in the truncation is allowed. There are some necessary conditions. Which I will say maybe in more details later on. Necessary.
Here you're assuming G is bigger than equal to N.
Yeah, so N is bigger than or equal to D. D is bigger than or equal to N, because otherwise it's 1. Yes. Yeah, so sure. I guess I should have said minimum. Yeah, but most of the time I will assume that D is bigger than or equal to N, but otherwise it should be the minimum. Yeah. So, okay, let me say a few of our results. So I'll just call this a proposition. So if you look at the set of all homogeneous polynomials in n variables of a fixed degree, you can think of that as a projective space. You take the coefficients, and that's the coordinates of my projective space. And then inside that projective space, we can look at the set of all such polynomials. So again, these fixed all homogeneous polynomials, all of fixed degree. I'm not going to write that, but that's the assumption. So the set of all such polynomials that have the pure threshold less than or equal to some number lambda, that's always a closed set in that projective space of all homogeneous polynomials. Closed set. And along these lines, it also follows that there are only finitely many values that can be achieved. I mean, that's also implicit in that statement, but I'm not assuming that is an isolated singularity necessarily. Just in general, there are only finitely many possible values. And that's essentially because this the set of values corresponds to the corresponding closed sets, and those satisfy both ACC and BCC. Now, the ACC is a theorem. I have this somewhere in my notes. I don't remember. The BCC is just because of the theorem. And also there is a. It's here. Oh, sorry. Yeah, sorry. And so there is a largest possible value, and moreover, the set where that largest value is achieved is going to be a Zariski open set because it's the complement of all the small values. So there is a largest value which is achieved. And so the set of polynomials where that is achieved is Zariski open. So we will refer to this as the generic value of the pure threshold. And that is the first theorem that I want to state, is a description of what this generic value is. So, I mean, you might guess that it has to be this, but it's not always this.
Does this fact immediately imply that there are no possible values in P minus 1 over P to 1?
No, the proof of this.
No, because.
Oh, okay.
Like, okay, just asking something like P squared minus 2 over P squared could be possible, right? Like, even if P squared minus 1 over P squared is not because of that.
And so, I mean, I guess what I wrote here does not automatically imply that, but if it goes with the proof, you'll see that it's not possible. And there's a more general statement there. I don't know how complicated the proof is. The proof of this is not complicated, but and what was I saying? So let's take a look at the generic value. So the generic value is, again, I'm not writing it anymore, but for fixed and BNP, the generic value is 1 if n is greater than or equal to b, which is achieved across the pure case. But if n is less than b, then what it is a truncation. I'll just write it this way. It's the truncation of n over bx part e, where e is a specific spot. It's the smallest integer, positive integer, such that d does not divide n times b to the e.
You have the lines?
And the remainder.
Do we want to pause or to get the
again? Sorry.
Do I need to do anything? Is there something we need to do to start?
There's a recording and a Zoom. And who is taking care of that?
Is it recorded? So that's not working, but here is recorded and streaming.
Okay, so I can start?
Yeah.
Okay. So, and the remainder, when we divide n times p to the e by d, has to be less than, well, I lost this note. Has to be strictly less than. That's the condition. So this is the generic value. It's the truncation at that specific spot. If such a e exists, if it doesn't, so that's also possible. If no such e exists, then the generic value is just n.
What is the truncation of a fraction?
So what you do is you write it in base p. So let's say it's alpha 1 over p, alpha 2 over p squared, and so on.
Okay.
Where the alphas are the digits, they're between 0 and p minus 1, and p1 is to be the non-terminating expansion. So if it terminates, you just make all the digits be p minus 1 from that point on, like 0.999. And then you take the first p of the digits. So, yeah, I never wrote it down, but sure.
It is important that it's the non-terminating expansion.
Yeah, the non-terminating. So meaning that there's infinitely many non-zero digits, no matter what. If no such exists, then it is analytic. So again, depending on what the arithmetic is between those numbers and the NP, if one or the other of the two situations might. Which is why we saw in the example that I wrote in the beginning that sometimes it was 5 over 6, sometimes it was a truncation of 5 over 6, depending on what P was mod P. I guess one comment about this is that there are certain circumstances where we can know for sure that no such E exists, and that kind of relates to the conjecture about infinitely many P's that I said in the beginning, but only in the sense of the generic value. So if you just look at the generic value, this shows that there are infinitely many P's where the generic value of the FPD coincides with the value of the local expression, which is the M of P. So let me just say that as an observation, if P is 1 mod P, then this cannot happen because n times p to the e is going to be n mod p. It's never going to be less than n. So then there are no such e's, and the generic dt is going to be equal to n over d, which kind of confirms the expectation that there's infinitely many p's where it's the same as the local expression. But again, we only have that for the generic. I mean, I have a sketch of the proof, but I'll try to be brief. So we identify polynomials. So I'm looking at f is written like this. And the AIs, so I is a multi-index. The AIs are the coordinates of my projective space. And then when we look at f to the power of n, the coefficients of that become polynomials in the AIs. We call them C and J. And J again is a multi-index. To the J. And the requirement for this f to the n to belong to the Frobenius power n to the p to the e is equivalent to the fact that all of these x to the power j that don't contain exponent greater than or equal to p to the e have to have coefficient equal to 0. So all of those coefficients have to vanish. That's kind of how we see that they are closed sets. So this condition would say this would be equivalent to the requirement that the FPD is less than or equal to n over p to the e. And that's if and only if all the coefficients are 0 for J, a multi-index that has all entries less than or equal to p to the e minus 1. Those are the ones where the x to the power is not in the Frobenius power of the maximal ideal. Now, where this condition comes in is that when this happens, I'm not going to go through that computation, but it is easy to see that there are no such J's. So when n times p to the e mod d is less than n, that implies that for all multi-indices of the appropriate degree, all of the monomials in the expansion automatically belong to the Frobenius power, and that's how we get that the f threshold is less than or equal to that quantity. But on the other hand, when this does not happen, then again, it's not hard to see that there are multi-indices where this happens, and moreover, if you look at these polynomials, they're not identically 0 as polynomials in the AIs. So for open set, they're not 0, meaning that the F threshold is going to be greater than quantity. And that's for all e's, meaning it's going to be greater than the limit of those quantities, which is a negative. So that's kind of the sketch, but I didn't really write it all down. Now, I guess what I consider our main result in that paper is this. Well, so then we focused on the case of two variables. And also on the assumption that the polynomial is an isolated singularity or reduced for two variables. And the statement of the theorem might not sound very impressive, but I think it is interesting. What we proved is that.
Sorry, can I ask you?
Yeah.
So what you were realizing there, isn't that a support of the conjecture you were mentioning previously? In the sense, in those cases, LCT is always an overlay, right? When you were saying, as
Yes.
long as you have infinite unity, you have that.
Yes.
So that is a support towards the one.
Yes, it is. Yes. It's the only problem is you can't hold it for a specific. It's generic. So it is not a priori clear that there are other values. Potentially, if you look at an isolated singularity, that's kind of a mild singularity, so maybe they all have the same generic value. Now, what we call extremal singularities of Frobenius forms, which Janet mentioned yesterday, those only occur for a specific value of d. If d is equal to p to the e plus 1, then we know that we have those extremal singularities. But for arbitrary d, is there such a thing? So that's what I want to talk about next. I'll just. Also, there are some assumptions that I need. I want to assume that d is greater than or equal to 4 and not divisible by p. Those are necessary conditions when statement is not true without those assumptions, then there exists reduced polynomials in two variables that have of degree b that have a smaller value. Strictly smaller than the n over the which in this case 2. So in particular, well, I guess we don't know whether the generic value is 2 over d or a truncation of 2 over d. One other observation which I didn't write down is that if d is even and n is equal to 2, this requirement would say that 2 times p to the e is 1 more d, and that's not possible again if d is even. So when d is even, we know, and then it's 2, we know that that's the generic value. And this statement in particular would say that there exist smaller values, there exist more singular choices of that. So the proof of that was really hard. And it's non-constructive. So, I mean, it's not hard to see that there are polynomials with a smaller value, but it's hard to see that there are any reduced ones. I mean, if you want to take just the power of the variable, you get 1 over d, but that's, we are not allowing those. So the hard part was to see that the locus where all those polynomials C and J that I described earlier vanishes is not contained in the locus of the non-reduced polynomials, which are the discriminant vanishes. So that was the output. I do want to say when d is smaller, when d is equal to 2 or 3, in two variables up to a change of coordinates, there's only one reduced polynomial. If the degree is 2, that's just x times y, up to a change of variables, and if it is 3, up to a change of variables, it's just x times y times x plus y. So in that case, there's no other choice. You only have one possible value for a reduced polynomial. Which is why we make this assumption. Also, when p does divide b, I don't know that we have looked into what exactly happens, but we know that when d is equal to a power of p, or 2 times the power of p, again, only the generic value is possible. Now I will tell you some more details about the restrictions in the Hernandez and co-authors paper on the possible places where the truncation can occur. So this is from this paper. And so they have n variables, and I think they're allowing non-standard gradings. But that has to be an isolated singularity. So the precise statement is it's the minimum between n over p and 1, or the truncation, and I mean, this is essentially n over b, but written writing a over b, which is the same as n over b written in lowest terms. So if b is odd, well, I'm thinking about n being 2. For me, n is 2. Meaning when d is odd, it's just 2 over d. When d is even, it's 1 over half of d. And d is the same as n over d. So and again, I'm assuming that n is less than d. Otherwise, Otherwise, I guess it's a truncation of 1, which is also possible.
Okay, they don't have a precise end.
So they give a list of conditions, necessary conditions that must be satisfied by this L, which is the start of the truncate, in order for this to potentially occur as a value. So the list of conditions, these 3 conditions. First one says, if P does not divide P, then L has to be less than or equal to the order of P as an element in the multiplicative group Z mod P. Multiplication. Condition 2 says if P is bigger than P, then for all E primes that are less than L, A has to be less than the remainder of A P to the power of E prime mod P. And there is also condition 3, which is very similar, but it's about the remainder of A times P to the L, that precise L. Here. Remainder of A P to the L mod B has to be greater than A, 0, and less than or equal to A. So the question that we had, and they also were raising this question in their paper, was are these necessary and sufficient conditions? So these are what they prove is that these are necessary conditions.
Excuse, do we have the recording text again? Okay.
This is 3 necessary. Conditions. So, question, are they also sufficient? Meaning, for every L that satisfies these requirements, is there a polynomial that has that variability threshold? And the answer is no. There's a counter example that we wrote in our paper. I mean, it's just an easy observation. So again, I'm focusing on 2 variables. If P is greater than 7 and D is 2P minus 3. So these situations where we don't get those values seem to be related to D being close to a multiple of P, I would guess, I don't know. But that's what we used to give a counter example. If you take L to be 2, it's easy to verify that those conditions hold. However, if you look at the truncation of 2 over B at the second spot in the base P expansion, it is 1 over P plus 1 over P squared, and this is in one of those what I call forbidden intervals. Well, not the same one that I had earlier, but the interval from 1 over P to 1 over P minus 1. That again, from that theorem of Liebman-Muscat and Smith, is known to be one of those intervals where no values of activity can occur. So this is the forbidden interval. But these exceptions seem to have something to do with the value of the degree being close to a multiple of P. And so the other thing that Karen and I did in our paper was we analyzed small values of the degree. We got up to degree 8, I think, and then I guess we stopped. But anyone could go longer potentially, I don't know. So what we did is up to degree 8, I guess a theorem, we checked that all the possible values that are allowed according to the Hernandez et al. Conditions actually do occur. So I don't say more of 2. about how that went. So your theorem was for B less than or equal to 8. And L that satisfies. So we made a list. Of course, the list depends on what P is. What P is more P more specifically. Satisfying conditions. There is a polynomial. Reduced polynomial. The threshold equal to the truncation of 2 over the L squared. Now, in their paper, they also looked at this question and they did give some examples. I think when DD is 5, they show that, again, there's a list that one can make of what all the possible L's are. And they did show that each one of those values occur, but they picked a specific value of P to illustrate that. So instead, we show that for every P, according to what P is, you have one list or another, but all of the values on that list do actually occur. And let me just say one word about how we went about checking that. So the theorem that I stated earlier, where we said that there are values that occur that are smaller than 2 over the guarantees. So sometimes the list is short enough that that theorem is enough. The non-constructive one that just guarantees the existence of a value that's less than 2 over b, sometimes that's enough. But in other cases, the list included a few more entries, and in those cases, we actually gave complete polynomials that have the required value. So I mean, I'm hoping that maybe somebody will be interested to see what happens next, because I mean, I'm not saying I'm guessing that this happens for most. Of course, there are exceptions, but yeah, I don't know what the exceptions are.
When you say L satisfying 1, 2, 3, are you like fixing an A and B?
Yes, the A and the B, the N over D. Yeah, so for a fixed N and for a fixed B. There's a list of, so I mean, I fixed the B to be one of the degrees of the element, and N is 2. Now we're only doing it in 2 variables. Yeah, so those are fixed.
Yeah, but I guess.
But the prime, the P is not fixed, the prime number.
Yeah. But are there a lot of A and B that you could like write these constructions with? Or down this, like.
I mean, I could write some explicitly. No, but A and B are just A is 2. I guess I should write about A and B. So because we are looking at the 2 variable case, N is 2. D is the degree, and then A over B, it just means N over B lowest terms. So when N is 2, depending on whether D is even or not, if D is odd, then N is 2, N is the same as A, and D is the same as D. And when D is even, then you can simplify A is 1 and D is that's it.
Okay, sorry, I misunderstood.
Yeah. But the one that varies is the P, and P can have different arithmetic behavior as far as what it is mod P, and that's what gives the various cases. Okay, that's all I wanted to say. Thank you for your attention.
Any questions? Is it obvious that P minus 1 over P minus 1 to 1 over P is a covenant interval?
Yes. What is the question? But
one
one
over
over,
p minus 1 to 1 over p, I get to forward an interval.
1 over p to 1 over p minus
1
1.
over p to 1 over p.
Yeah, and there's more general intervals like that are known.
I guess p power e, you can just do the same thing, like 1 by 1 over p power e.
Yeah.
It's not hard, it's not that easy though.
So for given n, b, and p, is there like an algorithmic way of finding out all the values or that's?
No, not that I know of. I mean, yeah, so there's a list of potential values
Yeah, but like,
that you can easily find. Sure. I mean, it's not hard to produce all the errors that satisfy those requirements.
So after ones that just forbidden intervals.
Other questions? You have like numerous examples of that, like that counterexample you gave of one that isn't realized. Do you have are there like families that are like that, or is that just one example?
We just did that one.
I think you could probably generalize it up.
Yeah, we didn't try, but yeah. We didn't do that, but somebody else should, I guess.
Any other questions? Okay, well then let's thank Adela again.